Hi, thanks for joining me. Today I'm going to be evaluating a really cool integral. It's the integral from 0 to infinity of 1 over x to the 4 plus 1 dx. But the way I'm going to be solving it will not use complex analysis and it will not use partial fractions. So those are probably the two most obvious ways to go about solving this integral. I'm going to be doing it using neither of those. Now before I get stuck into the video, I should say that Dr. Peyam has made a really good video in which he integrates 1 over x to the n plus 1 from 0 to infinity, where n is some positive integer bigger than or equal to 2, but that does use complex analysis. But if you're familiar with complex analysis, I really recommend you go and check that out as well. A link for that will be in the description below, but check it out once you've seen this video. Anyway, if you want to have a go at evaluating this integral here, have a go now, pause the video, but I'm going to get stuck into evaluating this without using complex analysis and without using partial fractions. Let's get stuck in. Okay, so firstly what I want to do is introduce a new integral which is even crazier than the one we started off with. It's the integral from 0 to infinity of 1 over x to the 4 plus 2x squared times cos 2a plus 1 dx. And here a is just some real number between 0 and pi over 2. Okay, so a is between 0 and pi over 2. So now this is even more interesting than the one we started off with, but notice when I put in a equals pi over 4, which is in this range certainly, this cosine 2a becomes cosine of pi over 2, which is 0. So then this integral here collapses to 1 over x to the 4 plus 1, which is the one that we're trying to work out. Okay, so what I'm going to do is firstly work out what I of a is, and then plug in a equals pi over 4, and that will give me the solution to my original integral. Anyway, how are we going to work out how are we going to evaluate this integral here, because it looks even crazier than the one we started off with. What we're first going to do is a very simple u substitution, and that u substitution is let u equal 1 over x. Okay, so that of course just means that x is equal to 1 over u, and then dx is just minus 1 over u squared du. Okay, so just taking this and plugging it back into this integral here, we get that I of a is equal to the integral of, now when x is 0, this thing here is 1 over 0, and it's sort of 0 plus, so 1 over 0 plus is positive infinity. And on the numerator, and the top of the integral, when x is infinity, u becomes 1 over infinity, which is just 0. So this thing here is a 0. And now for the integrand, the top still stays as 1, and the bottom, x to the 4, well that's just 1 over u to the 4. 2x squared becomes 2 times 1 over u squared, so plus 2 times 1 over u squared cos 2a, and then plus 1 is just plus 1, and then dx we know is minus 1 over u squared du. So let me just write that here, minus 1 over u squared, and that's du. Okay, now what we want to do is firstly notice is this minus sign here means I can swap the limits of integration. So let's just do that first, get rid of that minus sign. And this top limit becomes infinity, and this one here becomes 0. Lovely. And now what I want to do is just multiply the top and the bottom by u to the 4. So the top then becomes u squared, and the bottom, 1 over u to the 4 times u to the 4 is just 1. 2 times 1 over u squared times cos 2a, multiply that by u to the 4, that's just going to swap this thing here for a u squared. And then this plus 1 just becomes plus u to the 4. Okay, so we've got this integral here. So we've just expressed IA in a different way. But notice u is just a dummy variable. It doesn't matter what I replace it with. So I'm just going to replace the u here for x, which is perfectly fine. So this thing here becomes x squared. This thing here becomes 2x squared cos 2a. And then this thing here is just x to the 4. And then, of course, dx. Okay, so we've got IA also expressed in this way here. But notice this looks very similar to what we have up here, IA. So I of A equals this thing here, but it also equals this thing here. So what we're going to do is just add up both of those. So I of A plus I of A. On the left hand side, we just get 2 I of A. And now on the right hand side, we've got an integral from 0 to infinity plus an integral from 0 to infinity. So we can bring it under one integral. So it's the integral from 0 to infinity. And notice that the denominators are exactly the same. This one's just sort of written backwards. But it's x to the 4 plus 2x squared cos 2a plus 1, and it's the exact same thing here. So the denominator stays the same. So the only thing we need to worry about are the numerators. So it's just 1 plus x squared. Okay, so this is 1 plus x squared, all divided by this denominator here, x to the 4 plus 2x squared cos a plus 1 dx. Okay, so we started off with this integral and we've now written it this way here, and of course we've got this 2 here. Now what I want to do is bring this to the top of the whiteboard and we'll continue. Okay, so we have 2I of a equals this integral here, the integral from 0 to infinity of this guy here, dx. First thing I'm going to do is just divide both sides by 2. So I get this integral now is I of a is now half times this integral here. The next thing I want to notice is that this the integrand here, is a function of x, but in particular that function of x is an even function. So in other words, if I swap all the x's here for minus x, it's going to stay exactly the same. So we can use a nice little trick. The integral from negative alpha to alpha of an even function for any alpha is going to be exactly 2 times the integral from 0 to alpha of that function. So this thing here is precisely, so this integral here is a half times the integral from negative infinity to infinity of this guy here. So I can actually write this as an integral from negative infinity to infinity, then I've of course got to multiply by a half, so this half here just becomes a quarter. Okay, so I of a is a quarter times the integral from negative infinity to infinity of this guy here, dx. Now what I want to do is also use a similar trick, but with odd functions. So whenever we have the integral from negative infinity to infinity of an odd function, or in fact the integral from negative alpha to alpha of an odd function, that's always going to evaluate out to 0. Okay, so what I want to do is add 0 to this thing here, which obviously won't change it, but instead of adding 0, I'm going to add the integral from negative infinity to infinity of an odd function. Now, which odd function do I want to choose? Well, it's going to seem a bit arbitrary to start off with, but then you'll see why I've chosen that odd function in just a few lines' time. But the odd function I'm going to be adding on is essentially this thing here. So 2x sine a, and then divided by this thing here. So this integral IA before was just a quarter of the integral from negative infinity to infinity of x squared plus 1 divided by this thing here, dx. But now what I've done is I've added on minus 2x sine a divided by x to the 4 plus 2x squared cos 2a plus 1. And notice this sort of part here, this function is odd with respect to x. So that's just going to be adding on 0 because it's the integral from negative infinity to infinity. So this is perfectly fine. And again, I say we've added on this minus 2x sine a, and it's not quite clear why I've chosen that, but it will be clear in just a second why I've done that. What we want to do now is look at this denominator in a bit more detail and see if we can rewrite it. And the way we're going to be able to rewrite it is by using our double angle formulae. So we have x to the 4 plus 2x squared cos 2a plus 1. We know cos 2a is the same as 1 minus 2 sine squared a. Okay, so that's what I'm going to write down. Okay, and now all I want to do is expand the brackets on this thing here. So this is equal to x to the 4 plus 2x squared. And I'm just going to write this 1 here. And then minus 4x squared sine squared a. But now this thing here, x to the 4 plus 2x squared plus 1, that's a perfect square. This thing here is just x squared plus 1 all squared. Lovely. And this thing here is also a perfect square. It's 2x sine a all squared. Okay, and now we've got the difference of two squares. So this guy here is precisely x squared plus 1 plus 2x sine a, and then x squared plus 1 minus 2x sine a. Okay, lovely. Let's just remember this is just this thing here. So I'm going to replace the denominator with this guy here. So making this integral even uglier than what it started off to be. But I promise you things are going to sort of collapse nicely in just a second. So let's rub this out. And just replace the denominator with this guy here. So this integral now is a quarter times the integral from negative infinity to infinity of x squared plus 1 minus 2x sine a, all divided by this new denominator, x squared plus 1 plus 2x sine a, and then the other one here, x squared plus 1 minus 2x sine a dx. Okay, and you probably spotted x squared plus 1 minus 2x sine a cancels nicely with that guy there. So this thing here cancels with that thing there, and we're just left with the integral, or quarter, of the integral from negative infinity to infinity of 1 over x squared plus 1 plus 2x sine a dx. Now what we want to do is evaluate this integral here. Let's bring this to the top of the whiteboard and we'll continue. Okay, so now we've got I of a equals a quarter times this integral here, a quarter times the integral from negative infinity to infinity of 1 over x squared plus 2x sine a plus 1 dx. Now what we want to do is this integrand here, the denominator in particular, we can simplify by completing the square. So this thing here is just x plus sine a all squared minus sine squared a plus 1. Okay, but now you might notice 1 minus sine squared a, that's just cosine squared a. So this thing here is just this plus this. So I want to rewrite this integral using this sort of expression here. So we've got the integral is equal to the quarter times the integral from negative infinity to infinity of 1 over x plus sine a all squared plus cosine squared a dx. And now hopefully you might be able to realise what we're going to do next. It's just a nice u substitution, and we're on the final steps to evaluating this integral. We're going to do the u substitution. U equals x plus sine a and then divided by cosine a. Okay, so then this of course gives us that du is just 1 over cosine of a dx. Now I guess one thing you might want to just be careful of is this dividing by cosine of a. Is cosine of a 0? Well, it's not, because remember we said that a is between 0 and pi over 2, and we're not including the endpoint. So it's the open interval 0 pi over 2, so cosine is never 0 in that interval, so that's fine. So we've done our u substitution, let's plug it back in. It's a quarter, the integral from, well, when x is negative infinity, we're just doing negative infinity scaled, but because it's scaled by something that's not 0, it's going to remain we're scaling it by something that's positive, because remember cosine is positive between 0 and pi over 2. So 1 over cosine is positive between 0 and pi over 2. So we're scaling it by a positive number which is not 0. So this thing here is going to be minus infinity plus some constant. So it's going to remain minus infinity. The same thing holds for the top limit. It's going to also be infinity. And then this integral becomes 1 over x plus sine a squared is just cosine a times u squared. So it's just u squared cos squared a plus cos squared a, and then dx becomes 1 over cosine a dx is just cosine of a du. So this thing here is just, if I can squeeze it on, I'll rub this off and put it here. This integral here is equal to a quarter times the integral from negative infinity to infinity. In fact, it's 1 over 4 cos a. So just this cos a cancels with one of the cos a's in the denominator, so factoring the other one out, 1 over u squared plus 1 du. And remember the the antiderivative of 1 over u squared plus 1, that's just arctan. So this thing here is 1 over 4 cos a inverse tangent of u from infinity to negative infinity. When I plug in infinity, inverse tangent of u is pi over 2. And when I plug in negative infinity, I get minus pi over 2. So pi over 2 minus pi over 2 is just pi. So this thing here is precisely pi over 4 cosine of a. Okay, which is really nice. We now worked out what I of a is using this weird, convoluted roller coaster of a method of integration. But we worked out I of a is equal to pi over 4 cosine of a. And that's, I guess, a more general problem. But remember, if we go back, we wanted to work out the integral from 0 to infinity of 1 over x to the 4 plus 1, and we showed that's the same as the case when a equals pi over 4. So if I just get rid of all this mess, we have that I of pi over 4, which we know is the integral from 0 to infinity of 1 over x to the 4 plus 1 dx. This is precisely plugging in pi over 4 into that. So pi over 4 times cosine of pi over 4. Cosine of pi over 4 is just 1 over root 2. So we get pi over 4 divided by root 2, or divided by 1 over root 2, so we can put the root 2 in the numerator. This is just pi root 2 over 4. And we're done. That's our solution to the integral from 0 to infinity of 1 over x to the 4 plus 1 dx. Using this weird, I don't really know how to describe this method, because we started off by introducing this new parameter a, And generally when you do that, you want to differentiate the integral and, you know, bring the derivative into the integral and things like that. We did nothing like that. We used sort of trig identities, weird adding on odd functions, writing things as even functions, and a bunch of junk like that. But we managed to get to the answer. We started off with a sort of cute integral, this thing here, introduced this a term, made this integral uglier and uglier, then it cancelled quite nicely, used some completing the square trig identities, and we got our solution, pi times root 2 over 4. Anyway, I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.